What is it, Michel?
This is an Astro Tracker from a B-52 Bomber. The thing was designed in the 50s, I think.
Hello and welcome back. If you follow the channel, you might have seen our previous restoration of an analog electromechanical air data computer from a similar vintage, which was mind-bogglingly complicated, but worked amazingly well. This is in a similar vein, but part of an even more complicated and ambitious 1950s military aircraft superiority system, a Kollsman MD1 Astrocompass, an electro-opto-mechanical navigation computer using celestial object tracking. And we are delighted, I would even say relieved, to have Michel as a special guest all the way from France to help us out.
Hello guys.
In case you don't know of him already, Michel is the YouTube king of vintage avionics hardware reverse engineering on his channel Le Labo de Michel. Like us, he goes far beyond simply tearing down his drop-dead gorgeous items. He reverse engineers them, explains how they work, and makes them work again. I highly recommend you subscribe to his channel, link in the doodly-doo. Michel donated this Kollsman MD1 Astro Tracker unit to the channel and came over to help us work on it. Actually, more than that, he's going to lead the restoration and I'm going to try to keep up with him. The Astro Tracker, that was part of an Astrocompass system, which is super complicated, and it gives you your true heading, but it's navigation by stars. And we just took it out of its baggage, so we're discovering it. The base has to be maintained level. It's in the wing, right, of the airplane. It has to be maintained level by a vertical gyro, which we have here. Okay, well that would be interesting. Oh my, we haven't even cracked it open and I already have to start the elevator music. That's because I have to explain star navigation and the full system that our Astro Tracker belongs to, the Kollsman MD1 Astrocompass. This Astrocompass was flown on B-52 bombers and was a classified system. Here is the entire system in its full glory. You will recognize our pressure cooker / flying saucer contraption in the middle. That is the Astro Tracker proper. Notice that it also has a cylindrical canister on the side. That's the gyroscope unit that we are missing, but Michel brought us another one from a different system. We'll try to see if we can MacGyver the two together. On the left, you see the control panels. That's the part that the navigator would interact with. Here is a closer view. We'll explain what these all do in a minute. On the right is an impressive pile of tube electronics that we don't have either, so we'll have to recreate our own. You can't help but notice that there is also another mean-looking pressure cooker thingy at the bottom right. That's an important part of the system that we don't have either. However, Dave from the EV Block channel somehow got his sticky hands on one. He tore it down self-admittedly medieval style in his video episode 854, link in the doodly-doo.
And we're in like Flynn.
And wait to see what's inside. Oh yeah, it's a marvel of analog mechanical computing. We'll also explain what it does in a minute. By the way, I asked Dave if he still had it. Unfortunately, it appears that it did not survive the medieval attack. So if you have another one in your collection, please let us know. We'd be delighted to marry it, even temporarily, to our Astro Tracker. So what does that giant pile of complicated equipment do? It gives you your true heading, that is, the direction you are flying, by looking at stars or the sun. No, really, that's all it does, but with a precision of ±6 minutes of arc. So why was it so important to dedicate so much complicated hardware, which was classified by the way, for just knowing your heading? That's because in the pre-GPS days, that piece of information was essential for long-distance navigation, which itself is essential for long-distance bombing runs, particularly at night. In other words, having that extra bit of information could win you the war. Which gets us to the topic of astronavigation. In the 1950s, when GPS and high-precision inertial navigation did not exist yet, your primary navigation means was dead reckoning. Dead reckoning, or DR for short, works by integrating your speed and direction over time to maintain a running estimate of your current position. It's the refined equivalent of counting how many steps you take and in which direction to know where you are. Many amazing analog computers had already been developed for performing this integration calculation accurately. However, the problem with this technique is that any errors accumulate and grow with integration time. If the speed and direction inputs are slightly inaccurate, the estimated position error builds up the longer you fly, a big problem for the long-range B-52. One large source of inaccuracy is the wind. It's not enough to input airspeed and heading. What you really need is your ground speed and ground path direction, both of which are strongly affected by the wind. Some incredible devices had been invented to incorporate the effects of the wind. You can see some of them on Michel's channel. But winds are unpredictable, so even these heroic contraptions were bound to yield approximate results. Fortunately, by the 1950s, the ground speed problem was finally solved by Doppler radars mounted under the aircraft and pointing at the ground, which, you guessed it, you can also see on Michel's channel. Thanks to Doppler radar, one finally had a very accurate way to determine ground speed. Airspeed was also precisely known thanks to yet another analog computer, like the Bendix air data computer that we repaired in another series. So the only missing piece of the puzzle that was left is heading. Unfortunately, the traditional methods for obtaining heading weren't great. Magnetic compasses are not very accurate because the Earth's magnetic field is all over the place. Take a look at this isoconic line chart. It's an absolute mess. Unless you fly along one of the thick no-change lines, your magnetic compass is going to be pretty far off and goes totally bonkers when you fly near the poles. Gyro direction indicators were invented as a remedy. We demonstrated one in the previous episode and it was epic. It looked impressively precise, but unfortunately they all drift and you have to realign them to a magnetic heading every hour or so. So that's not a good solution for long-duration navigation either. That's when astronavigation came to the rescue. The principle was not new. It had been refined for hundreds of years for maritime navigation using a sextant to sight known stars. Astronavigation is simple in principle but quite complicated in practice. I'm going to try to explain it to you. Usually that means a long series of incomprehensible YouTube videos or a 400-page textbook, so I'll just try to give you enough for you to follow this video. A sextant is an optical instrument that allows you to measure precisely how high a star is above the horizon. The result is an angle that is traditionally called the altitude of the star, although it is an angle going from 0 degrees at the horizon to 90 degrees at the zenith, so not the traditional meaning of altitude at all. Anyhow, suppose that you are right beneath a star. Your sextant would measure an altitude angle of 90 degrees straight overhead. If you could calculate the star's celestial longitude and latitude at that very moment, that would also be your location on Earth, since you are right beneath it. In practice, there isn't a convenient star smack overhead, and you can't make a good angle measurement directly overhead anyhow. So you usually sight a known bright star, planet, or the sun at a more convenient oblique angle. The higher the angle, the closer you are to the projection of the star on Earth's surface. Note that a traditional sextant does not measure the horizontal direction of the sighting, known as the azimuth. So all you know from a sextant sighting is that you are somewhere on the circle around the star. So our intrepid navigators would take a second star sighting, defining another circle, and know that they had to be at one of the intersections between the two circles. Since the intersections are usually pretty far apart, it's obvious to tell which one. For aviation, where determination of heading is important or even primary, the sextants include an azimuth measurement ring at the base. Aeronautical sextants are things of beauty, and of course Marcel has a few in his collection. He let us play with a gorgeous Soviet instrument one day. In practice, the sighting technique is applied in reverse from what you'd expect. You use your best estimate of your current location and heading to calculate what the star azimuth and altitude angles should be. You then preset the sextant to the pre-calculated angles. This should get you close, and you will just need to slightly recenter the star at the pre-planned time. You then write down the angle adjustments you had to make, which are error terms. The azimuth error will give you the correction needed for adjusting the true heading. The altitude angle error will give you a quantity known as the intercept after a simple calculation. The intercept is the distance from your estimated position to your actual position, which you can then plot on a chart. This calculation is greatly simplified by the use of the nautical mile. Every minute of error angle is equal to exactly 1 nautical mile of intercept. There is a wonderful example on YouTube of a seasoned Boeing 737 crew using a manual sextant to find their true heading. In this case, they are flying over northern Canada, and because the magnetic compasses are so messed up there, they are required to recalibrate them when coming back south. They, of course, stubbornly refuse to use any of the far more convenient modern electronic methods like the GPS. Here is how you do it, the manly way.
As we proceed back into southern domestic airspace, we require that we reset our compasses to the proper magnetic heading. So, making use of the Air Almanac, which is for the proper year and the proper date, we can determine the sun's Greenwich hour angle and declination for the proper time. We've previously done our calculations for this date. We set in our declination of north 21 degrees. We've used our Greenwich hour angle of 136 degrees. We know from our maps that our longitude is currently 79 degrees west. We subtract our west longitude from our Greenwich hour angle. We get our LHA, or local hour angle, that we set into our Astrocompass. So local hour angle is set at 57 degrees. And as well, we set the north latitude. We're 64 degrees north latitude, so on the Astrocompass we set that in. The Astrocompass is then leveled, and it's turned so that the shadow falls in the proper location on the Astrocompass. Right in this location here. And then it's removed, and the true course, or true heading, is read from the Astrocompass, which is
98 degrees.
98 degrees true.
What you witnessed is exactly what our Astrocompass system does automatically, with far higher precision and in a continuous way. You might have noticed that there are 3 major steps involved in the manual method. The first step is to pre-calculate the expected star sighting angles, so that you can preload the sextant. The Boeing crew does it using an almanac of pre-computed values and some additional hand computations which they don't show. In our system, the calculation is done by our mechanical computer, the one that Dave so gleefully tore down. For that, it has to solve a spherical trigonometry problem known as solving the celestial triangle. And that's why you see all these mechanized arcs in the computer. The computer literally builds a miniature physical version of a triangle and then simply measures the unknown side and angle. The second step is to make the star sighting. That's what our flying saucer Astro Tracker does, which we also are about to gleefully tear into. But rest assured, no Astro Tracker will be hurt in the making of this video. Quite the contrary, we promise we'll try our best to restore it and make it work again. Finally, there's a bit of post-computation needed to extract the true heading and the intercept. The true heading is then electrically fed back to the very secret B-52 bombing system, which has the dead reckoning computer. It will now be far more precise thanks to the continuous true heading information. The system also calculates and displays the altitude intercept, but it is not used by the navigation system. It is merely a check on the accuracy of the dead reckoning system. It should stay close to 0, and the navigator will then have full confidence that the currently calculated position is accurate. You should now know enough for the control panels to make sense. Starting at the right, you have 3 star data displays. That's where you enter the sidereal hour angle, SHA, and the declination, DEC, of your chosen stars. Think of these 2 angles as the longitude and latitude of the star on the celestial sphere. During flight, you can select which star the system should use with the big star switch. The latitude and longitude indications are your current position. They are normally automatically updated by the dead reckoning system. But if it were to fail, you could set them manually and do traditional intercept plotting and navigation. The big round display is GMT, Greenwich Mean Time. The digital indicator is marked GHA, which stands for Greenwich Hour Angle of Aries. This is the angle between the Greenwich meridian on Earth and the vernal equinox on the celestial sphere. The vernal equinox is the 0 reference point for the star SHA angles. It moves at a slightly different rate than GMT due to Earth's orbit around the Sun. Its offset with GMT varies within the year, so you have to look it up and set the correct value on the day of your flight. The ALT dial shows the pre-computed altitude angle of the star sighting. This is the output of our EEVblog mechanical computer. The heading correction is the azimuth error read by our star tracker. It is used to calculate the true heading, the most important output of the system. The true azimuth is the azimuth of our star sighting, and the altitude intercept is the distance in miles between the estimated position and the actual position. Both are needed for the navigator to plot the true position on a chart in case of backup manual navigation. There you go, you can operate a B-52 star navigation system. But you probably shouldn't. Now, let's open up our star tracker. There is pressure in it, and it says do not remove, so that's what we're going to do.
Ah oui, il y a une...
Schrader valve or something.
Morning, Mark.
Hey, hi Eric.
How are you?
Well, we have a visitor.
Ah.
Hello, nice to meet you.
Hi, Eric.
Michel.
Michel, nice to meet you.
And we're about to let the air out of the big thingy.
Oh.
I hope that's the right wrench.
No.
I heard nothing. No.
No pressure.
Okay. So, torch. Yeah. Oh, it's going this way.
Ah, okay.
It's not moving an inch.
What if you just tap it around the rim with the mallet?
The mallet.
Just break it free.
Go for it, my friend. What was that? It's alive!
I think finally the gas is coming in. Oh.
There we go. Whee! Oh, yeah, there's some broken stuff in there.
So this is the capacitor here.
And this is some glass. So we have some pieces of glass, a cap. Well, that's good. We have to do some repair on it. And then the usual. Man, this is another beauty.
Wow.
The glass a bit annoys me.
Yeah.
Because if it's part of a corner of a prism or something. Yeah, it's a corner of an optical surface. So we got Master Ken joining the party. Woo! Yeah, off the camera. And Michel, you found where the shard of glass came from?
Yeah, so it comes from the dome. It is a part of the dome here. I would say it would be difficult to see with the camera. Here.
Oh, I see. Yeah, I can see it by E. It's the rim of the dome. So, which sort of makes sense, right? Because the thing it's a hit from the outside. There you go. I can see it. There was a hit from the outside and that thing. There you go. So the dome is actually glass. I thought it was, or maybe there is a plastic. Well, this is glass, and then maybe there's a plastic envelope around. So we keep using the dipstick.
Biomotor, generator.
Induction something. Amazing how they did the wiring with all the pins around, and then go to cables. The photomultiplier tube.
Yeah, we can see the back with the resistors here on that side. You can see the several resistors.
Which resistors?
The voltage divider.
You mean from the PMT?
For each pin.
Yeah, that's the
Each pin,
photomultiplier, so that's the sensitive, light sensitive thing. And there's a million synchros and motors and shutters. What's this piece?
So this is a photomultiplier tube.
And then that's where the light comes through from the optics. You see the wheel with a wire mesh into it. That's a chopper. There's a good date on the thing, and you would think it's from the 1950s or 40s, but no. 7983. Just fly this and space shuttle at the same time. This is the first time we're applying some power. We need to access the screw that's underneath here, and for that we need to rotate the platform, and for that we need to release the brake.
That moves nicely.
Is this where you want it?
Yeah, in order to.
Yeah, push it over that way.
Okay.
There you go.
They're
Yeah,
wired
it's
in
perfect
parallel.
now.
All right.
Excellent.
Can you get the
Excellent.
screw? Yeah.
It's a team job.
All right.
Oh, it's stuck.
It's stuck.
See?
Yeah, it's still
Still
held
connected.
up on this one. Oh.
So most of those
Okay.
connectors have snap rings, but I don't know about
You
the
need
high
to
voltage one.
desolder.
Ah. If it's soldered for hermeticity, then we're hosed. So we weren't really able to lift the platform. Actually, we were, but it was entangled with the connectors. So we've been spending the rest of the afternoon, the better of the afternoon, desoldering the cables from the connector. There is no other way to do it. And then we carefully noted how the connector was made, what the color is, and where it ends up on either here or there. So hopefully we can redo it afterwards. So I've done mine. What about you, Michel?
I am fine.
Compare the styles. Pretty similar.
It is a bit different, maybe.
Yeah. And that's when the restoration started in earnest and things became difficult. Under pressure not to mess up, and with Michel not fluent in English, we tended to revert to our native French when things got tough. A bit like pilots immediately revert to their native language when a mayday situation arises. Sorry for that, I'll close caption it so you can follow. Prends 3 minutes de repos. Faire le courrier des lecteurs.
Tu les as mérités.
Ok, t'es prêt, Michel?
Prêt.
On va démouler le truc.
Démoulons le cake.
Vas-y. Oui. Regarde, le truc est bien cassé là.
Et voilà.
And voila, we extracted our precious Cold War contraption without breaking anything nor mixing up wires. What a glorious piece of optomechanical engineering. We'll reverse engineer it and figure out how it works in an upcoming episode. See you then!